Right. Fourier series. See, let me just introduce you this Fourier series by taking a small idea. Suppose you want to send some information. Say you want to send some facts. The page you want to send, let us say, contains some information and also a speck of dirt, right? So what fax machine does in this case, the fax machine actually cannot distinguish between the information as well as the dust, right? It simply scans the page line by line and it transmits the information. Understand? Picking which bit of information is useful, which it needs a very sophisticated analysis, right? Picking which bit of information is useful needs a very sophisticated analysis. In fact, you see, a research on this kind of sophisticated analysis is started with the work of Joseph Fourier, right? So this is the diagram of, this is the image of Joseph Fourier. Understand, in 1807, uh, Joseph Fourier was simply trying to study temperature distribution in metallic bar, which is given with an initial temperature. He was trying to draw a curve of temperature with space or time, just as a nurse tries to draw the graph of temperature variation of a patient with time. But in the end, he discovered that he could construct or build a function or curve by adding a series of sines and cosines, which was a revolutionary idea at that time. Right? See, recall what he has done. He was trying to draw the diagram of, diagram of some function which he got from his research. And see, he realized that function can be represented as a series of sines and cosines. That's a basic idea for what you call this Fourier series, right? As you can see here in the diagrams, if you look at the left hand side diagram here, see the original graph is given in red color. That red colored graph can be approximated by adding infinitely many number of sinusoidal functions, sine functions and cos functions. Don't think sine and cos are only two functions. Understand, sine x, sine 2x, sine 3x, sine 4x, and so on. They are all different functions, right? Similarly, we have cos x, cos 2x, cos 3x, cos 4x, and so on. These are all, we can write such infinitely many number of functions by taking linear combinations of all those functions. I mean, for example, I'll multiply sin x with some number and then I'll add it to multiplication of something else to this sin 2x. Something like this. You see, a naught into cos x functions. Cos x is one cosine function, cos 2x is another cosine function, cos 3x is another cosine function. Like this, you can take infinitely many number of cosine functions. Along with them, you can also take certain sine functions like this, you see, and so on, plus b1 into some sine x, then b2 into some sine 2x, like this. You can take different functions and their coefficients. You can represent, Fourier's idea is this. We can represent any particular function as a linear combination of infinitely many number of what you call sinusoidal functions, right? Whether you take cosine functions or sine functions, we normally take them as what you call sinusoidal functions, right? Now see, we are just trying to represent those functions. I mean, whatever the given function you have, we are simply trying to represent those functions, in terms of these sinusoidal functions, right? As you can see here, when you are given a particular curve, here it is a square wave, you see. To represent that red colored square wave, we have used so many infinitely number of what you call sinusoidal functions. That's how the graph of blue colored one is, it is changing. And after some number of approximations, we got it as very much similar to the original graph. I mean, the red colored graph. Even as you see on the right side here, the blue colored graph is the original graph actually. We were trying to approximate, that particular original graph. That's how you see here, the number is changing here. The degree is changing here. In the sense, we are adding that many number of terms here. Okay. So we are adding up to A36 as well as B36. You see, A6, A7, A8, A9, A10, 11, 12, 13. They're all the coefficient numbers here. You see, we are adding that many number of terms in the series so that we can approximate the original curve by this, Fourier series. In simple, as you can understand now, Fourier series is infinite sum representation of a function as infinite sum of what you call sinusoidal functions. But see here what happened. In 1807, the French mathematician Joseph Fourier submitted a paper to the Academy of Sciences in Paris. He was doing certain research, and a paper related to his research was, submitted to this Academy of Sciences in Paris for presentation or publication. See in that paper, he has presented a mathematical treatment of problems involved in heat conduction. Right? I hope you are somehow aware of heat conduction from physics. Right? When one end of the metallic bar is applied with certain temperature, what happens normally? The temperature will be distributed from regions of higher temperature to the regions of lower temperature, isn't it? So when that process is going on, there will be a kind of temperature distribution. Fourier was trying to calculate at what time what was the temperature, at a particular time what is the temperature, right? At a particular instance of distance within the metallic bar, at that distance how much is the temperature. He was trying to calculate the temperature distribution within the metallic bar, but you see in the process he got it as what you call a partial differential equation, because temperature changes with space as well as the time, right? It changes along with the metallic bar and even along with the time, so that you can see temperature distribution is a function of two variables. And when he modeled it mathematically, he got a partial differential equation. And at that time, there was no adequate mathematics to solve that particular problem. So what he has done, he has proposed a new technique, what we have discussed till now. He has tried to approximate the original function by a series of sinusoidal functions, right? But see what happened those days. Although the paper was rejected, right? It was rejected by the academy actually. Although the paper was rejected for lack of rigor, it contained ideas that were so rich and widely applicable that they would occupy mathematicians in research to the present day, right? The technique proposed by Fourier was too much for mathematicians of the Fourier time to accept. They didn't even understand what he has proposed. Mathematics of that time was not so adequate to prove this kind of assertion. This was the lack of rigor that led the academy to reject publication of Fourier's paper. But the implications were not lost on Fourier colleagues. One surprising implication of Fourier's work was that many functions can be expanded in infinite series involving sines and cosines, right? This revolutionary idea sparked a heated debate among leading mathematicians of the day and led to important advances in mathematics. Understand, though Fourier series was found in the context of analyzing heat conduction in a metallic bar, it turns out to be very, very useful in analyzing what you call the signal processing. Therefore, it received lots of applications in communication theory and signal processing. For example, if you are given a function or a signal in the time domain, it transforms a signal in the time domain to what you call the frequency domain. In fact, by Fourier series, we get a list of amplitudes and frequencies corresponding to different sines and cosines. Mathematical operations which are difficult or impossible in the time domain become very, very easy or possible in the frequency domain. Usually, students try to ask me, what is the main advantage of Fourier series? In fact, you see, whatever the mathematical operations we need to perform on a function which is defined in the time domain, right, which is defined in the real life, we try to convert that into its frequency domain using what you call this Fourier series. When it is converted into what you call frequency domain, Whatever the operations we can perform on that, whatever the mathematical operations we perform on that, they become very easy, right? In the frequency domain, those functions, the original typical function will be transformed into a simple function. Thereby, we can perform mathematical operations quite easily. You need to understand, you see, nowadays, even in Google, if we just speak out, our computer can understand what we are speaking. Computer can recognize, even it is available in mobiles now, right? When we are speaking out, just it will be transformed into text. The sound signal will be converted into what you call the text, right? What kind of program we may have in between? We are just speaking out, and mobile or else a certain particular program is converting that into some text, right? Exactly, in this kind of transformation, we use what you call Fourier series, right? I cannot say exactly the same Fourier series, whatever we are discussing is useful, but there is a lot of advancement of this Fourier series. We are just discussing it now, beginning of the things we are discussing. But you see, this was developed in a very different ways. And all those techniques are now useful in many engineering techniques. Being an engineer, if you have no idea of what is Fourier series, you cannot really do excellent in your job, right? That's what I can say. Now see, why actually Fourier series? Now, as you understood, as we are discussing since few minutes, Fourier series is an infinite series representation of, a function in terms of sines and cosines, right? Fourier series is an infinite series representation of what you call, a function in terms of sine and cosine functions. Understand why again a Fourier, why again an infinite series is required. If you recall, we have already discussed, we have already studied about this Taylor's series expansion, isn't it? We have discussed about Taylor series expansion. When you are given a function, let us say f of x, we can write this function, as, let us say, if you are expanding this in powers of x minus a, if you are expanding it about x is equals to a, we write it like this: f of a plus x minus a into f dash of a plus x minus a whole square into f double dash of a divided by 2 factorial, and so on, right? We can write as many terms as you want here. It is also an infinite series. See what you have done here in the case of Taylor's series expansion. F of x must be a continuous and n times differentiable function. It must be a continuous and n times differentiable function. Then only we can write its series expansion like this. That too, we are writing f of x in powers of, some algebraic functions, x minus a whole square, x minus a to the power of n, and so on. So when you have a continuous and n times differentiable function, then only we can write this kind of series. But in nature, you see, when we are speaking, when we are, observing certain things, many things around us are in waveform, isn't it? Many things around us are in waveform. So when you have those kind of functions, representing those kind of functions in these algebraic polynomials is not a proper thing. So it is better to represent them in periodic functions, isn't it? So keeping that idea in mind, in Fourier series, though it is seen Taylor series expansion, when it is a periodic function, we cannot, we cannot expand it. When it is a discontinuous function, we cannot expand it. When it has some more number of maxima and minima, we cannot expand it. So keeping all those limitations in mind, Fourier series was proposed. When you have a function f of x which is to be expanded, we'll just try to express this function f of x as, what you call infinite series of sinusoidal functions. We'll just try to write it like this: a1 cos x plus a2 cos 2x plus a3 cos 3x, and so on, plus b1 sin x, then plus b2 sin 2x, and so on, right? We are just trying to represent the given function in terms of what you call periodic functions like this, right? Sin x and cos x, right? Fourier series is actually a more universal function, more universal series than what you call Taylor's series, as it applies to all continuous periodic functions and also to the functions which are discontinuous in their values and derivatives, right? Even when the given function f of x is periodic, or when it is discontinuous, when it has what you call, uh, certain finite number of maxima and minima. In all these cases, we can find what you call the Fourier series. And in fact, you see, Fourier series is also a very powerful method to solve ordinary and partial differential equations, particularly with periodic functions appearing as non-homogeneous terms. We had solved certain differential equations when we were in first semester. We had solved, differential equations, ordinary differential equations of this kind: f of d into y is equal to some right hand side function. When you have these kind of differential equations, we found, what you call complementary function and particular integral. So to find out the particular integral, we use, this right hand side function. When you have this non-homogeneous term q of x has what you call a periodic function, whatever the particular integral methods we have discussed, they are absolutely useless, right? We cannot use them when this q of x is what you call a periodic function, right? In that case, even if this right hand side function is also a periodic function, we can use this Fourier series to find out the solution of that differential equation. So anyway, it has so many applications. It has uh, plenty. I cannot say one or two. In everywhere, in every thing, whatever we observe around us, there is an application of Fourier series, right? So anyway, we'll just move on to find out the Fourier series of different functions. But see, before proceeding further, as we are representing every function in terms of periodic functions, let us once recall what is actually a periodic function. A periodic function, as you can see here, it is a function that repeats its values at regular intervals. For each interval, the same thing will be repeated continuously. Mathematically speaking, a function f of x is said to be periodic with period t if f of x plus t is equals to f of x. If you take, for example, sin x or cos x, they are all periodic functions of period 2 pi. Right? Now, let us ask ourselves one more question. Since few minutes, I was telling you, we can represent every function as an infinite series of this kind, right? But can we represent every function as in this way? No, there are certainly some limitations, right? See, when the function f of x has, when it satisfies certain conditions like this, we call them as Dirichlet conditions. When the function f of x satisfies, these conditions, when the function may be periodic, may not be periodic also, when even for some regular continuous functions also we can write Fourier series. When the function f of x is single valued and finite, right? Even if it is periodic, we can write the series expansion. If the function f of x has finite number of discontinuities in one period, right? Even if it has some finite number of discontinuities in one period, even if it has what you call, finite number of maxima and minima, then in such cases, we can write what you call the Fourier series expansion. What do you mean by this single valued? When you give certain input x to the function f of x must give you a unique value, right? The function values for any input, you can find f of x as a single value. Then it is a single valued function. And for no x, if you substitute certain x to this function f of x must be finite always. I mean, for no x, function value is infinity. If you take tan x, for example, if you define tan x in the interval 0, 2 pi, then at x is equals to pi by 2, tan x gives you infinite value. So for tan x, we cannot write the Fourier series, right? If you take, for example, root x, when you take x is equals to 4, root x gives you plus or minus 2, isn't it? So that is not a single valued function. In such cases, we cannot write what you call the Fourier series. But even if it has finite number of discontinuities, or if it has finite number of maxima minima, even if it is periodic, we can write what you call the Fourier series, right? Now let me just mathematically define what is actually a Fourier series. Now, as we are discussing, a function f of x can be defined in the interval c comma c plus 2 pi, can be expressed as a trigonometric series. Understand? Since all these are trigonometric functions, we are calling it as a trigonometric series. Moreover, you see what functions we are using here, both sin x as well as cosine functions, sine and cosine functions. As we know, sin x and cosine are 2 pi periodic functions. That's why while writing the Fourier series expansion, whatever the function you are considering here, f of x, this function must be defined in an interval of length 2 pi, right? These functions f of x must be defined in an interval of length 2 pi like this. That's how you see I've taken the interval as c comma c plus 2 pi, right? So when you define this function f of x in the interval c comma c plus 2 pi, then f of x can be expressed as, you can see, infinite sum of all these sinusoidal functions, right? See, for this we have taken a constant here. See, when it is cos x we have a1, when it is cos 2x we have a2, then when it is cos 3x we have a3, and so on. Similarly, there must be some cos 0x, right, for which the coefficient is a0. As we know, when it is cos 0, it's 1. Since it is 1, it was not written here, right? And anyway, this 1 by 2 is the idea given by Fourier. So 1 by 2 into a naught plus all these things. So this kind of representation, we call it as a Fourier series, right? In a summation form, these things can be written like this. You see, 1 by 2 into a naught plus summation from n is equals to 1 to infinity. If you write all these things together, it can be written as an into cos nx, right? When you write these things in a summation form, as we had seen series earlier, we can write it as n is equals to 1 to infinity bn into sin nx, right? See, while writing this as the Fourier series, the only difficulty is how to evaluate these coefficients. These cosine or sine functions are already known to you, but what combination gives us the actual function? What combination exactly approximates the given function? In fact, you see, expanding the given series in Fourier series is nothing but approximating the original function by this infinite sum. We are actually approximating the original function f of x by this infinite sum. So when you are approximating, we must take certain values to these coefficients a naught, an, and bn. Evaluating those coefficients itself is the problem now, right? So whatever the function you are given, we need to choose certain coefficients which gives us that particular function f of x, right? That's how you see we call these coefficients as actually Fourier coefficients. And as I told you, now to represent Fourier series of the given function, the problem is only to evaluate these three coefficients a naught, an, and bn. In fact, you see, when you are given the function f of x, which is defined in the interval, let us say 0 comma 2 pi, right? Earlier you see I took it as c comma c plus 2i. If you take c is equal to 0 in particular, we'll get this interval as 0 comma 2 pi. Now I've just taken such an interval for understanding. When you are given a function which is defined in the interval 0 comma 2 pi, corresponding to that function, as you can see here, we can write what you call the Fourier series, right? So this is the series representation a naught by 2 plus summation n is equals to 1 to infinity an cos nx plus bn sin nx. When that is the series, as I told you, the problem is to evaluate its Fourier coefficients a naught, an, as well as bn. So we can use these three formulae. These formulae were proposed by uh, uh, one of the mathematician of that time, Euler, right? There was some idea given by Fourier, and Euler gave what you call a mathematical idea behind evaluation of these three coefficients, right? So we call these three as Euler's formulae or Euler's formulae, whatever is okay. And here you see he has given an idea to evaluate these three Fourier coefficients as certain integrals. Okay, by evaluating these three integrals, we can calculate what you call these three Fourier coefficients. And of course, after getting the Fourier coefficients, by back substituting them into this formula, we can write what you call the Fourier series. Understand, when the given function is defined in the interval 0 comma 2 pi, we got this as what you call the Fourier series expansion. In case when you are given a function f of x which is defined in the interval minus pi comma pi, look at it, even the length of this interval is also 2 pi. And don't think like always we want the interval of definition to be 0 comma 2 pi. I'm saying length of that interval must be 2 pi. In fact, you see, we extend that idea. Whatever the length of interval we are taking is 2 pi, that can be extended to an arbitrary interval also, right? We can write Fourier series expansion of a function in a simple random interval. We have intervals of this kind, 1 comma 2, 2 comma 3. Even in these kind of intervals also, we can write the Fourier series. But to understand the things quite easily, we are just starting with this 2 pi length intervals. Okay, now when it is 0 comma 2 pi, we have written Fourier series like this. In case if it is the interval minus pi comma pi, then also we can write the Fourier series. You see, you'll understand the basic difference here. This is how normally we write the Fourier series expansion: an into cos nx plus bn into sin nx. This is quite simple to, you can easily remember this. But here a naught is 1 by pi into, look at this carefully, when the interval of definition is 0 comma 2 pi, we have integrated this function between 0 and 2 pi. But now the interval of definition is minus pi comma pi. Therefore, I'll integrate this between minus pi and pi. That is the major difference here. The remaining all remains as it is. Right? You see, an can be calculated with this formula: 1 by pi into integration from minus pi to pi f of x into cos nx dx. Then similarly, we can evaluate bn. It is 1 by pi into integration from minus pi to pi f of x into sin nx dx. Right? So like this, when you are given a function f of x, depending on the interval of definition, we just define these three integrals and we just evaluate those three Fourier coefficients, and then by back substituting them into the formula, we can write what you call the series expansion. Right? So that's how we can write Fourier series expansion of a function which involves different sinusoidal functions. Right? See, we need to remember these results, more very important results, which are highly useful in simplification, simplifying what you call those Fourier coefficients. In particular, you see here, rule 3 and rule 4. We use, these two very frequently in almost every problem. Because see, while evaluating the Fourier coefficients, we are simplifying certain integrals. And while simplifying the integrals, we need to substitute either pi comma minus pi or 0 comma 2 pi. Isn't it? Where you are substituting in again sinusoidal functions only, sine or cos. That's how we frequently use either sine n pi or sine 2n pi, cos n pi or cos 2n pi. We need to remember these formulae, these values very importantly. Right? We use 3 and 4 almost in every problem. Okay, we use others also, but a little later. Okay, so keep them in mind. Now let me move on to a question. Let's take this question. Try to finish it quickly. Look at the question. Find the Fourier series. Find the Fourier series to represent f of x is equals to x square in the interval 0 comma 2 pi. Right? The function what you are given here is x square. I'm just trying to represent x square as an infinite sum of sinusoidal functions. That's what the Fourier series is. So I'm just I'm rewriting what you call the formula. The Fourier series is f of x is equals to a naught by 2 plus summation n is equals to 1 to infinity. I'm using only a single summation for convenience. an cos nx plus bn sin nx. You can write even summation to these two terms individually. You can even write summation an cos nx plus summation bn sin nx. Anything is okay. Now, what are these three coefficients here, a naught, an, and bn? Where a naught is equals to, it is 1 by pi into, see the interval is now 0 to 2 pi. That's why I'm writing it as integration from 0 to 2 pi f of x into dx. And what is an? An is equals to 1 by pi into integration from 0 to 2 pi f of x into cos nx dx. bn is equals to 1 by pi into integration from 0 to 2 pi f of x into sin nx dx. Right? So I'm just trying to use these three formulae to evaluate those three Fourier coefficients. So therefore, now let me first evaluate what is a naught. A naught is equals to, I'm just using the first formula, 1 by pi into integration from 0 to 2 pi. The function what you are given is x square. So I'm just substituting x square here, integration of x square dx. As we know, when we integrate x square, we'll get it as x cube by 3. Isn't it? Integration of x square is x cube by 3 with the limits from 0 to 2 pi. Now, when you substitute the limits here, see what happens. 1 by pi into, first of all, you need to substitute what you call the upper limit. If you substitute x is equals to 2 pi, we'll get it as 2 pi whole cube. 2 pi whole cube means it is 8 pi cube divided by 3, minus, if you substitute x is equal to 0, the lower limit, we'll get it as 0. So that what happens here, you see, therefore, in the next line here, therefore a naught is equals to, see how much you'll get here, it is only 1 by pi into 8 pi cube by 3. So you can cancel 1 pi, right? 1 pi can be cancelled, and therefore we'll get a naught is equals to 8 pi square by 3. Let's keep this aside. Now let me just consider the second one, which is an. An is equals to, as we know now, the formula is 1 by pi into integration from 0 to 2 pi. What is f of x? It is x square into cos n x dx. All of you please concentrate on this, how I am evaluating integration of this product. So it is equals to, I'm just writing this 1 by pi as it is. One can easily understand it's a product of two different functions, x square and then cos n x. When you have a product of two different functions, to integrate the product, we can use what you call integration by parts, correct? But see, out of these two functions in the product, when one of the function is an algebraic expression, we can use, instead of integrating by parts, I'm saying we can use integration, successive integration, Leibniz rule of successive integration. We can use that, you see. It is only when one of the function in this product is algebraic expression. See, what can we do using that? In the product, while integrating, I'll first keep this first function as it is. As we know, in this product, first function is x square and cos n x is the second function. So first of all, I'm keeping x square as it is, but I'm integrating what you have this second function. See, the second function is cos n x, so I'm integrating that. Integration of cos n x is sin nx divided by n. Fine. Next, we'll take minus. Alternately, we take my plus minus. Then see, from the second term onwards, we'll get nearly 3 or 4 terms, you see. In all these terms, you see, from the second term onwards, we try to differentiate the first function, but we try to integrate the second function, right? Always, we try to differentiate the first function and try to integrate the second function. We'll integrate the second function, except in the first term. But see what we did in the first term here. While integrating in the first term, we kept this first function as it is, but we integrated only the second function. But from the second term onwards, we are going to differentiate the first function and integrate the second function. So when you differentiate, now the first function is x square here. If you differentiate this first function x square, we'll get it as 2x. And if you integrate, this whole function, including the denominator n, if you integrate this whole function, as we know, integration of sin x is minus cos nx divided by, you will get actually one n, but already there is an n, you see. When you multiply those two n's, we'll get it as n square in the denominator, right? Now again I'm taking, you see, plus. First term we have plus, then I took minus, and again now I'm taking plus. Now see here, the first function is 2x, so we need to differentiate this 2x. What happens, when you differentiate 2x, it is 2, and then if you integrate this second function, now the second function is all this. When you integrate that, we'll get it as minus sin nx divided by, you will actually get n, but already here you have n square, n square into n, it becomes n cube, right? Remember, next to this, in the next term, now the first function is 2. We need to actually proceed like this, minus, because you see plus, minus, plus, and then now it is minus. We need to differentiate this 2. But when we differentiate 2, we'll get it as 0, 0 into, anyway something happens here. 0 into something, it is anyway 0. Not only here, even the subsequent terms become 0 only. When you get a constant here, all the remaining subsequent terms will be zeros only. Because they are all zeros anyway, I'm not writing them, and I'm only stopping here. Right? The limits are from 0 to 2 pi. Right? One more point, you see, I'm just now substituting 1 by pi into, see what I'm doing. I'm substituting x is equals to 2 pi. So it becomes what you call 2 pi whole square. So I'm writing it as it is 2 pi whole square. And here if I substitute x is equals to 2 pi, we'll get it as sine 2n pi. For convenience, I'm writing like this, n into 2 pi. So it is 2n pi by n minus, in fact, you see here also there are two minus signs. When you multiply those two minus signs, it becomes plus. Then here if you substitute x is equals to 2 pi, 2 into 2 pi, it becomes 4 pi. And what you have here, it is cos 2n pi divided by n square. Then plus into this minus, minus 2 times sine, if you substitute x is equals to 2 pi, it becomes sine 2n pi divided by n cube. These things you will get when you substitute the upper limit 2 pi. So I'm just writing it again for convenience. Now see, whatever you have substituted is all upper limit minus, now let me substitute the lower limit 0. When you substitute, you see, if you substitute x is equal to 0, we have x square actually. If you substitute x is equal to 0 here, it becomes 0. 0 into that value, it is something 0. Then here also you see minus into minus plus. What you have here, it is 2x. If you substitute x is equal to 0 here, even this also becomes 0. Therefore, the second term is also 0. But here you see the third term, plus into minus, it is minus 2 times. What happens here, you see, if you substitute what you call x is equals to 0, it becomes simply sine 0, which is 0. Right? So, what remains? 1 by pi into, recall, when it is sine 2n pi, even here also it is sine 2n pi. As we know, as we had seen in the previous slide, when it is sine 2n pi, its value is 0. Therefore, the first and even the third term both become simply zeros. So here what remains, you see, plus 4 pi into, what is cos 2n pi? We had seen just before, cos 2n pi value is 1. So we'll get it as 1 divided by n square, and the remaining terms are all simply zeros. So that you see, we get it as 1 by pi into what you call 4 pi by n square. And here this pi can also be cancelled, therefore we'll get an is equals to 4 by n square. So you can understand when it is a1, it is 4 by 1 square. When it is a2, you can understand it as 4 by 2 square. When it is a3, it is 4 by 9. When it is a4, it is 4 by 16. Like that, you can evaluate all the coefficients of cosine functions. Now, similarly, let me evaluate, the coefficients of sine functions, which is bn. Right? I'm just trying to finish it quickly. Now, see, again, I'm considering, you see, bn is equals to the formula 1 by pi into integration from 0 to 2 pi f of x into sin n x. F of x is what? X square into sin n x. Right? See, as how I did earlier, in a very similar way, here also I'm just trying to evaluate what you call this integral, because this is in product, and even one of the function is what you call the algebraic function. So it is 1 by pi times, see how I'm evaluating this. In the first term, I'm writing this x square as it is. I'm writing x square as it is, but I'm integrating what you call this cosine function, sine function. When I integrate this sine function, see what happens. Integration of sine nx is minus cos nx divided by n. Right? Then minus, I'm differentiating now x square, which is 2x. And if I integrate this cosine function, we'll get it as minus integration of cosine function is sine nx divided by n. Actually, you will get, but already here is one n. So we'll get it as n square. Then see plus, when you have 2x, its differentiation is 2. And then when you integrate this minus sine nx, see, when we integrate sin nx, we'll get a minus cos nx. Already here is also a minus sign, because of that it becomes plus cos nx divided by, already here we have n square, and after integrating, we'll get one more n. So when you multiply them, we'll get it as n cube, right? As I told you, you see, we also continue this minus, when we differentiate 2, we'll get them as zeros. Since all the remaining terms are zeros, I'm not writing them. I'm only stopping here. It is from 0 to 2 pi. Now see, understand, as we discussed earlier, when you substitute n is equals to 2 pi, x is equals to 2 pi, this second term here, it becomes sine 2n pi, right? If you substitute x is equals to 2 pi here, the second term becomes minus sine 2n pi. When it is sine 2n pi, it is 0. Surely it is 0. Not only for the upper limit, even if you substitute the lower limit x is equals to 0, so it becomes a sine 0, isn't it? It becomes a sine 0 and its value is again 0. So for both the lower limit as well as the upper limit, this term gives you only what you call zeros. So I'm just ignoring this second term here. In our further simplification, anyway, since they are zeros, I'm simply ignoring them. So what happens if you ignore them? 1 by pi into, I'm now first substituting the upper limit, 2 pi. So if you substitute x is equals to 2 pi, it becomes 4 pi square into minus, here if you substitute x is equal to 2 pi, it becomes cos 2n pi. When it is cos 2n pi, its value is 1, so we'll get it as minus 1 by n. And the second term, we have already ignored it. Anyway, its value is 0. Then see the third term, 2 into, here also if you substitute x is equal to 2 pi, we'll get cos 2n pi, right? As we know, the cos 2n pi value is 1 divided by n cube. Then see, these are the values for upper limit. Now minus, if you substitute the lower limit, 0. Because we have x square here, you see, when you have x square here, and if you substitute x is equal to 0, it becomes 0 only. So 0 into this term, it is also 0. And already we had seen, the second term we have ignored it. In fact, it is also 0 plus this 2 by n cube. In fact, you see here, if you substitute x is equal to 0, it becomes cos 0, which is 1. So it becomes 1 by n cube, 2 times 1 by n cube. So I'm writing it as 2 by n cube. Right? So therefore, it is equals to 1 by pi into, if you write all the terms here, the first term here we'll get is minus 4 pi square by n, and here it is plus 2 divided by n cube, then minus into this plus, it is minus 2 by n cube. So we can cancel these terms, you see, and the remaining is only, therefore, bn is equals to, see here if I write it, 1 by pi into minus 4 pi square by n. So we can cancel a pi, you see here. When you cancel that pi, we'll get it as minus 4 pi by n. So we got, you see, what you call the coefficient of sine functions bn. Now let me just substitute these coefficients in the formula, and that gives us Fourier series of the given function. So therefore, f of x is equals to 1 by 2 into a naught. See how much we got a naught? It is 8 pi square by 3. I'm substituting that here. It is 8 pi square divided by 3 plus summation an into cos nx. See how much we got an? It is 4 by n square. I'm just substituting, you see, 4 by n square into cos nx. See, the series is an into cos nx. So I'm substituting an is equal to this. Then plus summation, we can write it separately or together. Anything is okay. Bn, how much we got? You see, bn minus 4 pi by n into sin nx. Right? So if you just simplify this, therefore, the Fourier series of f of x is equals to x square is, see how much it is, x square is equals to, I'm just writing all this, if you divide 8 pi square by 3 by 2, we'll get it as 4 pi square by 3, then plus summation, I'm writing this together, 4 by n square into cos nx minus, you see here we have a minus, no, that minus I'm writing out of the summation, minus 4 pi by n into sin nx. So here n takes values from 1 to infinity. So this is, what you call the Fourier series representation of x square. As we know, x square is a very simple function, but still we are representing that simple function as an infinite sum of different sinusoidal functions, right? So that's how you can evaluate the Fourier series of any function, with these Fourier coefficients formulae.